Dear students, today we will study the important terms used in UV spectroscopy. Chromophore. What is an chromophore? Chromophore is the molecule or a functional group which absorbs electromagnetic radiation in the UV visible region. For example, carboxylic group. Carboxylic group absorb radiation due to N2 pi star transition. Lambda max for this transition is 280 millimicron is observed, and molar absorptivity constant for this functional group is 15. Another functional group which absorb radiation pi to pi star type of transition. For example, ethylenic linkage. For this, lambda max range is 170 millimicron and epsilon value is 14,000. Now, what is auxochrome? There are certain groups attached to chromophore which shift the lambda to longer wavelength. Those groups which when attached to chromophore and cause lambda to shift to longer wavelength, those groups are called auxochrome. For example, our benzene molecule absorbed lambda at 225 millimicron. But if we attach NH2 group to the benzene molecule, this NH2 group cause resonance with the pi electron of the ring. As we know that nitrogen has non-bonding electron, these lone pair of electron comes under resonance with the ring electron, and that shifts the lambda max to 280 millimicron. So NH2 group act as a auxochrome here. The substituent groups which produce shift in the lambda are given some special terms in UV spectroscopy. For example, if a substituent group attached to the chromophore cause lambda to shift to longer wavelength region, then that shift is called bathochromic shift. Bathochromic shift means lambda shifted to longer wavelength region. If lambda shift to shorter wavelength region, that shift is called hypsochromic shift. Means shift to lower wavelength. Now, if a substituent group cause shift in the intensity of the peak, if intensity of the peak gets higher due to the presence of some group attached to the chromophore, that shift is called hyperchromic shift. Increase in intensity of peak. If a substituent group attached to the chromophore cause a decrease in the intensity of the peak, that decrease in intensity of the peak is called hypochromic chromic shift. So this is how the chemical environment affects the UV absorption spectra. Now another factor which shifts the lambda either to the shorter wavelength or the longer wavelength, that is the presence of conjugation. What is conjugation? Conjugation is the presence of alternate single and double bond. If conjugation is present, conjugation means alternate double and single bond. It shifts lambda to longer wavelength. What is the reason why conjugation shift lambda to longer wavelength region? Reason is that conjugation causes delocalization of the electron. Delocalization means this electron is now in resonance with this double bond. This pi bond can be delocalized to this bond. Like this, there is resonance. So due to delocalization of pi electrons, delta E decreases. If delta E decreases, then lambda increases. This fact can be better understandable by the example. For example, we have given a question that identify these three compounds. These three compounds are CH2, and we have given the value anonymously. Lambda equals to 176 nanometer, 211 nanometer, 215 nanometer. A, B and C compound now we have to identify these three compounds, which compound will absorb at which wavelength. As we can see example A. In example A, there is no conjugation. As there is no conjugation, it means there will be no delocalization of electron. So it will absorb at least wavelength. While there is in B and C compound, there is presence of conjugation. There is double, alternate double, single and double bond. Double, single and double bond. But these two compounds are geometrical isomers. As this is cis and this is trans. We have already classified 160 nanometer. Now we left with two values, 211 nanometer and 215 nanometer. So B compound, as it is cis, it will absorb radiation at 211 nanometer, while C absorb at 215 nanometer. Lambda comes out to be higher, 215 nanometer. Now we will discuss Woodward rules for calculating lambda max in conjugated dienes, trienes and polyenes. There are certain rules to evaluate the lambda max. The values given by Woodward. Later on, these rules were modified by Fischer. First, we will discuss the Woodward rules. Woodward rules, given the values, some fixed lambda max value, basic value, which if we select parent open chain diene, means we have chain, carbon chain, then basic lambda value will be 217 nanometer. If we have heteroannular diene molecule, then we will take value 214 nanometer. If we take homoannular diene, then we will take value 253 nanometer. If we take there are double bond in conjugation, then for each double bond extending conjugation, value added is 30 nanometer. And there, if there are presence of substituent on the parent diene molecule, for example, if we have alkyl group, then for each alkyl group, value added is 5 nanometer to the basic value of lambda max. And if there is exocyclic double bond present outside the ring molecule, then each double bond value added is 5 nanometer. And if there, in addition to basic diene, triene, polyene molecule, there is presence of some oxochrome as a substituent, then we will add for OR molecule 6 nanometer, for SR molecule 30 nanometer, and for halogen we will add 5 nanometer value. For example, we have question, calculate lambda max in UV spectrum of 2,4 hexadiene. Now how we will evaluate lambda max for 2,4 hexadiene? We will use this table. We have to remember these values for exams. First we will draw the structure. Hexadiene molecule means we have 6 carbon. 1, 2, 3, 4, 5 and 6. 2,4 position is this one. 2,4 hexadiene molecule. The basic value for this diene molecule as it is an open chain diene molecule, basic value of lambda max is 217 nanometer. Now this is our basic diene molecule selected for the lambda max. Now on this diene, basic diene chain molecule, we have 2 alkyl substituent, 1 alkyl group and 2. There are 2 alkyl substituent molecule on the diene, basic diene molecule. So 2 alkyl substituent. So value will be added 5 for each alkyl group. 5 nanometer value will be added to the basic lambda max. 5 multiplied by 2 equals to 10 nanometer. So total lambda max for 2,4 hexadiene will be 227 nanometer is the answer. Another example we will discuss, that is the calculate lambda max for the given compound. This bond which is present outside the ring is called exocyclic bond. Now in this molecule we will select this basic molecule, basic diene molecule. For this, as it is not a part of the ring, it is an open chain diene. So basic value of lambda max will be 217 nanometer. Now we have to see whether there is alkyl substituent or exocyclic bond or conjugation is present or not. For each factor we will add the particular value from the Woodward rules. Now if you see, this is an exocyclic bond present in the compound. For there is one exocyclic bond. So lambda value corresponding to exocyclic bond will be added to the basic lambda value. Another thing which is present in the molecule is the alkyl substituent on the 1 and 2. There are two alkyl substituents present. So corresponding to two alkyl groups, we will add value 2 into 5 means 10 nanometer to the basic lambda value. So total lambda max of this molecule will be 242 nanometer is the answer.